Today, we're going to continue our theme of area and volume. We're still going to be using volume is cross-section area multiplied by height. Our assumption is going to be the same that it always is, or our complication is the same that it always is in calculus. We want to do multiplication, but one of our factors will be continuously variable. We're going to solve this problem the same way that we always solve this problem. We're going to assume that our continuously variable factor is in fact constant for some small change in the height in this case. We're going to make sure that we do this the single variable calculus way and that the shape, the cross-sectional area, always has the same shape, just variable size. Then we're going to do all the things that we've done so far. We're going to write everything, write that cross-sectional area in terms of our delta variable. We'll make sure that we define our delta variable, indicating where 0 is and which direction is positive. And then we'll turn our volume of the slice to a total volume in a definite integral and then calculate. Sounds super fun. With that in mind, let's consider this problem. We have a cylindrical tank with a radius of 3 feet and a length of 7 feet. I just realized how kind of weirdly dimensioned this is. It's 6 feet wide and 7 feet long. It feels like it should be longer. Oh well. It's custom made, so to fit some particular purpose. And it is oriented in such a way that the circular sides are perpendicular to the ground. Now, if we had oriented this 90 degrees the other way and made the circular sides parallel to the ground, this would have been a lot easier because instead of the length of the cylinder being 7 feet, the length of the cylinder is 5 feet, the depth of the water, because we just want the cylinder-shaped water. The reason that I turn the cylindrical tank on its side is to get a calculus problem out of this. So if we think about looking at this from the side, we have a circle. Now, this is going to be just the view from one end, so I don't have to try to draw a cylinder. But what's going on is we've got a cylinder with a circular end perpendicular to the ground. And there's water. So the radius of the tank is 3 feet. So the height of the tank is 6 feet. The length of the tank is 7 feet. And there's water to a depth of 5 feet. So there's water, there's like a foot of space up at the top. So there's water to a depth of 5 feet. I want to draw a picture of what's going on at the end. We have a radius of 3 feet. We have a length of 7 feet, which is coming out of the paper or going down into the desk, your choice. And there's water to a depth of 5 feet. So it's 3 feet, 3 foot radius, so 6 foot diameter. And we have water to a depth of 5 feet. So like I said, if I had oriented the tank the other direction, we just be calculating the volume of the cylinder. But here we've got a cylinder and the top piece has been cut off. So I don't have a nice circle of water. Now we could just use our formula for the area of a truncated circle, but I don't remember that one from geometry class. We can only do whole circles in geometry class. So this is because in geometry, they didn't want to tell you that the only area you need is length times width. You're just using pre-packaged what? All right, we need to make, but we wanted, so we turn the cylindrical tank on its side so that we can get a calculus problem out of this. Now, we want to calculate this volume by slicing. Now, when we slice it, we have to make sure that our slice always has the same shape. It can vary in size, but it always has to have the same shape. Now, if we knew what the area of a truncated circle was, if I knew what the area of a truncated circle was, where the whole thing was 6 and we cut out 1 unit from the top, I could just take that area and multiply by 7. But we don't have that. Does anybody have that formula? I usually forget to ask. Anybody know what the formula for, like, offhand? You've had like 10 seconds to think about it, so you don't remember that? Like I said, no one taught you that shit back in geometry because they're like, well, we'll just let calculus catch that one. And so here we are. They didn't even tell you that this was going to be a problem, did they? Oh, sons of bitches. Didn't even tell you what was coming. Oh, sorry, it's 2023. They didn't want to give you a spoiler for content. Maybe that's the frame. I don't know. So here's how it's going to work. We're going to slice this horizontally because I don't know the area of this truncated circle. I probably should, but I don't. I don't even know which one is the minuend and which one is the subtrahend. So what the heck do I know? Now, if we slice this horizontally and then draw this at a 3/4 view, if you draw this from a top view, if you draw the top view of the cylinder, it's just a rectangle. We can't see, if we take out this round part, the top view of a cylinder is just a rectangle where there's 6 going this way and 7 going this way. And on this one, we can't quite see the roundness going up and down, but the water is to a depth of 5 feet. And so we can see it's going to catch the sides at some point and just kind of have the shape of a rectangle. So that would be like the surface of the water. We can't see the 5. I can't label the 5 because the 5 is going up and down, either coming up out of the page or down into the desk. Since we can't see anything at all, I must have drawn it down into the desk. So that's why we can't see all the writing. Otherwise, we'd have 3D writing coming out. I did this at a clear desk once. It was much more convenient because you could see the numbers written under the desk. That's all beside the point. Now, at the very top, we don't really have a rectangle. We just got this one line of water. But as that would be like corresponding to this very top up here. But as the water goes deeper, we just keep getting these bigger rectangles, biggest at the diameter, at the center of the circle, and then they shrink down to another line at the bottom. So we always get these slices of water that are rectangles. So our slices are rectangles. Where we have a width and a length. Now, the width of the rectangle is the part that's variable. It looks like the length of all these rectangles is always going to be 7. So that's what we want to do. We want to think of this cylinder as a stack of rectangles. Cylinder is a stack of rectangles. I'm going to draw a rectangle down here. In this view, we don't see the 7 feet going down into the desk. All we see is the width of this rectangle. Our strategy is going to be the same as it always is. I'm going to just take this area and assume that it does not change for some small change in variable, in this case, height. That I will label delta x. So the volume of my slice will be the area of the cross section multiplied by the height. The area of the cross section is just 7W, 7 for the length and W the variable width, and the height is just going to be my delta variable, delta x. But I can't integrate W with respect to X because I know W and X are related. So I have to figure out what that relationship is between W and X, which means I have to define where X is, which means I have to wonder why I drew this circle so friggin' small. Especially when I have my cool circle tool. Gotta pick one. All right. So let's see what's going on. We've got our radius. I missed. Damn it. Here's our radius of 3. We got a length of 7 that we cannot see, and we've got water to a depth of 5. And we've got a slice of water down here with a width. And we're going to use that width for some change in X. So there's our slice of water. And this has a certain width. In this picture, this red line represents that rectangular slice of our cylinder. The volume of our slice is going to be 7W times delta X. I need to write W in terms of X. That means I need to write this variable. I need to be able to track this width going up and down this cylinder. So I need X to be something up and down. Here's my delta x variable, and this is the squish direction of my delta variable. So x is going to have to go up and down. There are, well, as usual, there are an uncountable infinity of places we can put our variable. There really are only 1, 2, 3, 4 that make sense. There are only 4 places to put the variable that makes sense in this scenario. We could go with the top of the tank, or the bottom of the tank, or the center of the tank, or the surface of the water. So we have 4 reasonable choices. Because I know how this problem is going to go, I am going to pick the center of the tank. I'm going to let x be the distance from the center of the tank down to the slice. This is because I know what I'm going to be doing with my, to get this relationship between W and X. Setting X up in this location has done certain things. We're not done defining X, because when we decide where X is going to go, we have decided where X is 0. We have decided the positive direction. And in this case, positive is the down direction. So down here at the bottom of the tank, X is equal to 3. Up at the top of the tank, X is equal to -3. More importantly, for our purposes, the surface of the water is at -2. This happened because of the way we define where X is and the way we've drawn our diagram. Here's how we're going to get a relationship between X and W. I'm going to use the main thing that I have, and that the side of the tank looks like a circle. For contrast. And I'm going to grab this right triangle. The reason I want to grab this right triangle is that it has X in it. It has not W, but has half of a W. And it's got a nice constant hypotenuse. So in this triangle, the hypotenuse is always at the radius of the circle. So the hypotenuse is 3. This vertical leg is X, and this horizontal leg is 1/2 of W. So I'm going to use the Pythagorean theorem to get a relationship between X and W. Half of W squared plus X squared is 3 squared. And so we can solve this for W, and W will be 2 times the square root of 9 minus X squared. If you see this square root of 9 minus x squared and say, hang on, this looks like it's going to show up in our integral. And we're going to have to thus do trigonometric substitution. You are correct, partially. Because our focus last week was on doing trigonometric substitution. Our focus this week was on finding volume and making sure that our volume formulas work. So we're going to black box the integration at this point. But I've got an expression that relates W to X. So I can put that into our volume of the slice. The length is a nice 7 feet. Our width in terms of X is 2 square roots of 9 minus X squared. And our height is delta X. Our slice is a rectangular solid, so it makes sense. We're not surprised that we just have length times width times height. Now that we've got a formula for the volume of the slice, we finished our development phase. We can turn our development into a definite integral and write our total volume. I'm going to take the 14 out of the integral. And we're integrating the square root of 9 minus x squared. In the definite integral, the discrete delta x becomes the continuous dx. And it's green still. And we're going to integrate everywhere there's a slice of water. Now, if we look at the diagram, with x defined the way we have it, the water starts at -2 and ends at 3. So the 5 feet of water that we're going to be integrating, that's where the depth of the water shows up, is we're going to go from -2 up to 3. Now, to integrate this integral, we would have to do trigonometric substitution, but y'all have already proven you have trigonometric substitution chops, or you will soon. I think I forgot to put a due date on that homework, but that's all beside the point. That's just like the business end of things. Y'all have already proven and verified your trigonometric substitution chops. You've got that ability. So now we're going to do the problem with machine help. I want 14 times the integral of the square root of 9 minus x squared with respect to x from -2 to 3. So I want 14 effing integrals of square root of 9 minus x squared dx from -2 to 3. And there's our volume, 176.24. Typically, what I'll do in these problems to indicate that you don't have to do the integration by hand is I will say round your answer to 5 significant figures. I will request 5 significant figures, even if it doesn't make any sense at all to request 5 significant figures. You're going to be like, oh, dude, why are you asking for 5 significant figures? There's one. There's one. The hell, man. I'm gonna go quiet, save those kind of complaints for physics and engineering. This is math class. I want 5 significant figures because if you got a correct answer to 5 significant figures, you did not guess. So we get 176.24. I mean, we're doing the problem in cubic feet anyway. As if a cubic foot of water has any kind of meaning to visualize. Now, the problem with this problem is that I only partially filled the tank. So we've got the integral from -2 to -3. we should check to see that this is going to give us the things that we expect. The entire volume of the tank is going to be pi times the radius squared times the radius squared times that one times 7. That's the whole volume. We should get this same value if we integrate our integral, not from -2 to 3, but -3 to 3. That would be the top of the tank to the bottom of the tank. So if I redo my integral from -3 to 3, we get the same value. Note where the values changes. And remember that we're doing approximations. This is pretty good evidence that we are okay. The reason that we would want to check our integral against this is that this is something we can independently verify with the formula for the volume of a cylinder. Whereas the 176.24 is only something that we could verify against the answers in the back of the book. We should make sure that this is not a fluke because we might be suspicious of this difference down here in these far decimals. If I had the tank filled halfway, half of 197.92 is 98.96. So if I integrate, let's say from 0 to 3, this should give us half of the volume of a cylinder. And it does, 98.96. Once again, it's nice and consistent all the way down to, well, it's through 4. 1, 2, 3, 4, 5, 6. 6 significant figures for 10,000. So if you're concerned about this difference is happening because of the way the calculator approximates its definite integral. So we're okay. So we verified our answer, not against the answer in the back of the book, but we checked it against, we used our definite integral to calculate some things where we know what the result should be. Any questions? Remember, the last thing on our list of things to do is to come up with the answer. That was not the point of the problem. The point of the problem was setting up a definite integral. And the point of doing this problem was to give you something that wasn't similar triangles to create a relationship between stuff going sideways and stuff going up and down. And also to make you think about definite integrals, thinking about where you put your variables. Those are the things I care about. That's why I only fill the tank partially with water, because I want to make sure that you're integrating in the right place. Any questions? How's everybody okay? So a question did come up. There is a significant question here. Notice that I said, remember I had mentioned there are an uncountable infinity of places we could put the variable, because I always say that. I don't know why. But there are only 4 that made sense, and I picked one for you. So you're like, oh, dude, how are we supposed to know which one to pick? If I had The Rock here with me, this is why I want him to guest host, guest lecture on today, a day like today. I would have to plant someone in the audience that raise their hand and say, but Professor The Rock Johnson, how do we know which one to pick? But before you got to the end of that question, you'd be like, oh, how do I know where to put the, he bursts in and says, it doesn't matter where you put the X. And at that point, that would be kind of the purpose of having Professor Dwayne "The Rock" Johnson standing on one day. I would just be like watching this on a video feed and be like, oh, yes, that's what I was waiting for. So I picked this one for you. What if we put it somewhere else? It might be important. What if the density is a function of X coming from the surface of the water? So let's deal with that. What if the variable is somewhere else? So I'm going to grab my, this should be a sponsored post. If this is a sponsored post, I could show you the back of my Iris drawing tool by Maker's Cabinet, but it's not. So dang it, I just did. I'm just kidding. This is one of my favorite. This is one of my favorite things that I've kickstarted. So so we've got all the same stuff. This is 7 coming out. I got to pick a point up here. I'll just use this line here for my 5 feet for the water. I'm going to put the slice down here. Some of you may have noticed that positive was down because I wrote the slice down here. What if I put the slice up here? In case you're wondering, that'd be the question that I wouldn't be answering. I'll be like, oh, good question, and then just kind of move on. So let's suppose that I called this delta y because this is the alternate universe where we always use y. Notice a lot of these things are the same. I still want the width of this slice. It's still 7 long. Well, let's say I put my y somewhere else. I want y to be the distance, the depth of the water. Let's just put the slice at the depth of the water. Or sorry, put y at from the surface of the water, the slice at the depth. So when we define a variable, we don't just get to label stuff. We have to tell ourselves, remind ourselves where things are. When I put y here, I have decided that 0 should be at the surface of the water. The center of the circle will be at 2. The bottom of the tank will be at 5. The top of the tank will be at -1. When you define a variable, you're deciding where 0 goes and which direction is the positive direction. So once again, I set positive as being down. One side is 0. The other side is the slice. The slice is in the positive direction. To get a relationship between this y and w, we're going to use the same triangle we used in the previous formulation. The reason that we want to use the triangle here is that we want to use the constant radius of our circle. This is the only place that we can draw a right triangle where the hypotenuse will always be 3. I have to use the center of the circle. Down here underneath the horizontal side is still 1/2 of the width. But this side, this vertical side of the triangle is not the variable that's in play. In the previous formulation, that was just x, but here that's not x. The distance from 0 to the slice is at y, but I have to subtract off the 2 feet from the surface of the water to the center of the circle. So this distance here is y minus 2. So now we have a different relationship between w and y. So in this case, I have a half w squared plus y minus 2 squared is equal to 9. So w will be 2 times the square root of 9 minus y minus 2 squared. At this point, since we are also well versed in the technique of integration by substitution, we can see how one's integral will substitute right into the other. If I let x equal y minus 2, then I can turn the integral that I'm about to, I forgot, I didn't write this integral down yet. Then I can turn the integral that we're about to write down into the previous integral. I'm going to pull the 14. We'll integrate the square root of 9 minus y minus 2 squared. My discrete delta y becomes my continuous dy. But in this case, we're integrating not from -2 to 3. The 5 feet of depth we're integrating is from 0 to 5. That's where the water is in terms of y. Then I'll punch this into my calculating machine. And we get the same thing, 176.24 cubic foot. The important thing here is that we're trying to get an up and down variable to go with a left to right variable. And the vehicle that we use when our cross section is a circle is that the hypotenuse, if we draw a right triangle from the center of the circle, we'll always get that constant hypotenuse. If I tried to draw a right triangle from the surface of the water, my hypotenuse would not be a constant 3. We have to set it up, then we'd have just 3 things running around. And that's what's known mathematically as an unsolvable mess. Also note that this integral will substitute into our previous integral. If we let x equal y minus 2, then dx is equal to dy. And we would also have to change the endpoints. When x is equal to 0, oops, sorry, when y is equal to 0, then x is -2. And when y is equal to 5, then x is equal to 3. So substituting the y minus 2 for an x would just change the dy into a dx. And instead of integrating from 0 to 5, we'd integrate from -2 to 3, just like we did in the previous problem. The other big takeaway from the student standpoint here is that if you found this problem in print or let's say on a quiz on Canvas, I would have said round your answer to 5 significant figures. And that is your cue to not do trigonometric substitution to calculate this integral. That's your cue to go directly from the definite integral to your answer. Round your answer to 5 significant figures is my cue to say, hey, use a calculator on this one. Any questions? Comments? Deep thought? All right, let's see, today is Thursday. So that's gonna do it for today. That's gonna do it for this week. Tomorrow is Flex Time Friday. So take an hour that we would normally spending in class, catch up on some of the old videos, look for some other videos. Otherwise, do some work on your own on Fridays. I'll be in my office from 9 to 11 like normal. That's it for today. I'll see you all on Monday. Everybody have a good weekend and thanks for playing.